Next, we'll become a little more familiar with the Special Satellite Microwave Imager Sounder, or SSMIS. In particular, we'll focus on the imager and take a first look at polarization of radiation. Radiation appears in two basic polarizations, horizontal and vertical. The polarization refers to the propagation of radiation through an electromagnetic field. Vertically polarized radiation, in some frame of reference, has this electric field oriented vertically, such as the red line indicates in this figure at the top. The magnetic field runs perpendicular to the electric field. As seen in the animation on the right, when radiation in one horizontal dimension is emitted out of phase with its propagation in the other horizontal dimension, x and y shown here on this plot, then the radiation is circularly polarized. Radiation can take on left-hand or right-hand circular polarizations, as seen in the animation, which demonstrates the propagation of 4 different types of polarization. The circular polarizations can be defined as either clockwise or counterclockwise, depending on whether defined from the point of view of the emitter or the observer. As we mentioned in the previous module, the emissivity of the ocean changes as a function of many factors, including its temperature, salinity, the frequency of radiation emitted, or the roughness of the sea surface. It is also dependent upon the polarization of the radiation emitted. Objects including the land or ocean surface emit radiation simultaneously with various polarizations. In this figure, we see how emissivity of the ocean varies simultaneously with angle of incidence on the x-axis from a smooth, flat ocean surface, frequency with 2 different frequencies shown, 60 GHz and 10 GHz, and polarization with the top 2 lines denoting vertical polarization at the 2 frequencies. An incidence angle of 0 degrees means that radiation is transmitted vertically. We see that in this case, emissivity is not dependent upon polarization, but that the emittance at 60 GHz is about 30% more than it is at 10 GHz. And this is just talking about the angle of incidence being 0, where the emissivity is not dependent upon polarization. As the angle of incidence increases, however, the vertically polarized radiation is more effectively emitted than the horizontal, while the emittance of horizontally polarized radiation also gradually decreases. Typically, microwave remote sensing is done at incidence angles of less than about 60 degrees. Next, we'll work through an old example of microwave brightness temperature observed in a wintertime scene from the late 1900s. These were observed by SSMI before the sounder was added. The imager operated in 4 frequencies, 19, 22, 37, and 85 GHz, and in orthogonal polarizations. These are similar to the bands used on the imager on SSMIS today, and which is the focus of the lab on passive microwave imagery in this class. It operates at the same frequencies, essentially, but the 85 GHz band is replaced by a band at about 91.6 GHz, which is sometimes referred to as both the 91 or 92 GHz band. The SSMIS also detects emissions in the oxygen band near 55 GHz to 60 GHz. The image shown at top left is an example of 19 GHz vertically polarized brightness temperatures observed over the northeastern portion of the Soviet Union and nearby ocean. In short, we can call this the 19V channel, 19 vertically polarized. Brightness temperatures over the ocean are generally low, while brightness temperatures over land are relatively warm. The yellow line near the top of the image is the northern shoreline of the landmass, and the warm temperatures to the north of the coast are emissions from ice, sea ice in particular, and we'll see this more clearly in later bands. In comparison, and note the change in the color scale here, the 19 horizontally polarized channel, or 19H, shows lower temperatures over the ocean than in the vertically polarized channel of the same frequency. So you can flip back and forth between these two and see that. 2 locations over the ocean, which were also faintly seen in the 19V channel, here's one and here's another one right here, show slightly elevated brightness temperatures. Just looking at the 19 GHz channel, these may indicate locations where the wind is roughening the surface, or locations where cloud is quote-unquote replacing some of the emission from the poorly emitting surface with emissions from the relatively good emitting cloud. As we move to 22 GHz, the contrast between land and ocean remains, but some clouds become apparent. Some of the warmer brightness temperatures over ocean, like this and some of this out here, and the lower brightness temperatures over land might be caused by cloud. It turns out certainly the ones over water are, as we look at later bands or higher frequency bands. The emissivity of the 22 GHz radiation is the same in the vertical and the horizontal polarizations, so only a vertical channel is used. At 37 GHz, the sea ice, which is a relatively good emitter compared to liquid water, has the highest brightness temperature in the whole scene. The ocean brightness temperature is higher than in 19 GHz because the ocean is more emissive at 37 GHz. But it is lower than at 22 GHz because more surface emissions are absorbed by oxygen in the atmosphere at that band. At 37 GHz, clouds over the ocean begin to become more apparent, and some spots with lower brightness temperatures become evident over land, which depend largely on the emissive properties of the land surface in those particular locations. At 37 horizontal, noting again that the color scale changes, we see again that brightness temperatures are generally cooler than in the vertically polarized channel. Finally, when we look at higher frequency data, in this case at 85 GHz, we're first able to notice that the spatial resolution is much higher than before. We can see details that we didn't before in their lower frequency channels. Individual cloud features aligned in a band are now clearly visible offshore. The clouds are shallow, however. We know this because their brightness temperatures at 85 GHz are warmer than the surrounding ocean in clear sky environments, and the ocean is still a poor emitter. However, because high frequencies are particularly susceptible to absorption by water vapor, the 85 GHz brightness temperature in cloud-free areas over the ocean is higher than it was at low frequencies. Again, this is because fewer emissions from the poorly emissive ocean are able to reach space unaffected by atmospheric constituents. We also notice that the land has a much lower brightness temperature at 85 GHz than at the lower frequencies. Here, the brightness temperature is no more than 200 Kelvin, while in the 19V channel it was 240 to 250 Kelvin. Emissivity of the land generally decreases from 19 to 85 GHz. However, the land in this case may be also covered by snow partially, which has emissivity that can vary as a function of the snow density as well. Most fundamentally, though, a lot of the variability you have seen in brightness temperatures is related to the variability in emissivity of the surface, or variability in the amount of radiation emitted by the surface that is able to pass completely through the atmosphere. And finally, we can look at the 85 GHz channel in horizontal polarization, which highlights many of the features shown on the previous slide, although a different color bar is again used to highlight some of the variability over land, which we can now see much like we did at 37 GHz. We'll spend a little time now looking through some of the specifics of data collection as pertaining to SSMIS. It, like many other low Earth orbiting satellites, is in sun-synchronous orbit. The equatorial crossing times vary by satellite and evolve over time, but are generally in the afternoon and on the ascending node. The scan geometry of the sensor is shown in this figure. It scans in a cross-track configuration at an angle of 45 degrees off nadir, meaning that it sweeps back and forth in arcs along the surface that are perpendicular to the flight track. A sweep back and forth is denoted by the curved black lines. As the satellite moves along at an altitude of over 800 kilometers, it quote-unquote paints in a swath along its track, and the width of that swath is about 1,700 kilometers. Within that swath, it collects data at various frequencies previously mentioned. Therefore, The microwave sensors, unlike the geostationary sensors, observe only a small location relative to the geostationary instruments over the same time period. Because the emissions of microwaves by Earth are low compared to IR, the spatial resolution of microwave data, despite the sensors being closer to Earth than, for example, GOES, is lower than geostationary data or low Earth orbit in the visible and IR wavelengths. The spatial resolution also depends on the frequency in the microwave, with the higher frequencies that are a little closer to Earth's peak Planck emittance having higher spatial resolution. Three ellipses here are shown to scale relative to each other. A larger footprint is required at low frequency channels such as 19 and 22 GHz. Therefore, data is rather coarse, 69 by 43 kilometers nominally at nadir. However, a relatively small footprint can be used at 92 GHz, which is similar to the 85 GHz channel in the old SSMI. You can see the ramifications on the different spatial resolutions by looking back at the previous slides of sample data and comparing the details you can see in the various frequencies. SSMIS also uses a sounder, which is the last S in the acronym, to gather information about profiles of temperature and moisture. The fundamental mechanism for how these quantities are derived is the same as for other infrared sounders or microwave sounders, like those on JPSS platforms. The SSMI sounder bands are located near two absorption bands. The first is the oxygen absorption band near 60 GHz, covered by the bands down here at the bottom, and a few bands on the other side at the very top of this table. The other is a water vapor absorption band, close to 200 GHz. And you can see those on the plot of the absorption spectrum in the microwave as well. The two sets of bands are useful for estimating, respectively, profiles of temperature and humidity in the atmosphere. Approximate weighting functions of the modern-day SSMI bands are shown here. On the left are the weighting functions for channels surrounding the oxygen absorption band. These allow for estimation of a crude vertical profile of temperature in both the troposphere and the stratosphere. On the right are the average weighting functions of the imager channels, as well as the bands centered well above 100 GHz. These are more useful for deriving profiles of water vapor in the troposphere. Solid versus dashed lines in this figure show differences in some of the upper atmospheric weighting functions for polar versus tropical regions. Several products can be derived from the SSMIS brightness temperatures when used collectively. 1/2 day's worth of swaths for one satellite are shown here. This figure shows column integrated water vapor derived from the multiple bands used for water vapor detection. It represents the mass-weighted integral of water vapor present in a column. The red colors represent large values of water vapor, which are mostly present in the deep tropics. Other products include surface wind speed, where, for example, we can see the magnitude of winds in mid-latitude cyclones really pop out. You can also see cloud liquid water. Some frontal boundaries or other features in the mid-latitudes are readily apparent, as well as precipitation, or rather, clouds that could lead to precipitation in the tropics. And the rain rate, which is closely related to the cloud liquid water in many locations. Finally, products like this map from the University of Wisconsin are derived for the entire globe hourly. These use data from a combination of different sensors, including those aboard the various DMSP satellites, the SSMIS instruments, to create more continuous estimates of atmospheric humidity. A network of various microwave sensors aboard numerous platforms substitutes for the lack of temporal resolution that a single satellite can provide at any location. This is an instantaneous multi-satellite estimate of atmospheric water vapor. And it looks similar to the monthly average derived from just one satellite, which is what is shown here. This shows, again, like the water vapor plot before, how much moisture is detected, and you see that peak in the tropics especially. We're able to estimate this by leveraging the extinction of radiation in the atmosphere that is emitted by the surface. For example, in two equally warm environments, and using a frequency that is sensitive to water vapor absorption, which is essentially all bands except those in the oxygen absorption band, the moisture environment will often yield higher brightness temperatures over ocean, telling us that more water vapor is present and allowing us to make this type of product. And finally, this plot corresponds nicely with this last one, the monthly average estimated rain rate from the same single satellite. And it provides some insight into a key aspect of tropical dynamics. That's the relationship between tropospheric moisture and moist convection, where most of the moist convection, particularly in the tropics, falls where you see these warm colors. ITCZ, South Pacific Convergence Zone, the tropical warm pool where SSTs are quite large. And then you also see mid-latitude tracks, at least during this particular month in January 2019.